Hey everybody, I just wanted to do a little review of the digital numbering systems. We've been looking at 4 different types of numbering systems. The most common is our decimal, and then we talked about binary, octal, and hexadecimal. Now these numbering systems all have different bases. For example, decimal has a base of 10, which means we have 10 numbers altogether, including the number 0. The base is also called the radix. So for binary, we only have a base of two numbers, 0 and 1. Octal is a base of 8. 0, 1, 2, 3, 4, 5, 6, 7 is the highest number in octal. And in hexadecimal, we have a base of 16. What's interesting about this one is that we actually count up to 9, and then we convert to the alphabet. So A, B, C, D, E, and F. And A represents 10, B is 11, C is 12, D is 13, E is 14, F is 15. If I took a look at a decimal number, we'll just get familiar with it. 432 is the one I picked. Now the most significant digit is the 4. It's the biggest number. The least significant digit is the 2. For example, if I was buying a stereo, I'd be more interested in this first number, the 4, because that represents the hundreds, than the 2. When we look mathematically what 432 means in decimal, 2 is the ones, 3 is the tens, 4 is the hundreds. And we could also look at it like this. So we have 2 ones, and 10 to the power of 0 actually is equal to a 1. So anytime we have to the power of 0, it's going to be a 1. For example, 10 to the power of 0 is 1, 2 to the power of 0 is also 1, etc. So 2 times 1 would give us a 2. The tens is 3 times 10 to the power of 1, which is just 10. And 3 times 10 is 30. And then 4 times 10 to the power of 2, which is basically 10 times 10, times the 4 would give us 400. Add all of those guys up, and we come back to 432. Now, binary is very similar, except remember we only have a base of 2 numbers. So the highest number that we can go to ever is a 1. And this is the very common base that we use in computer systems. If I look at it relative to what I just did with the decimal system, I had my binary number here is 0, 1, 1, 1. And I put the little 2 down there to represent that it's a base of 2. And so 1 times 2 to the power of 0 is the same as 1 times 1 down here. My next significant number is 1 times 2 to the power of 1, which is just 1 times 2. Then we have 1 times 2 times 2, which is 4. And this one was a 0, so it's 0 times 2 times 2 times 2, or 0. Add all of those guys up, and voila, I've actually come back to a decimal number. So I've converted this binary number to a decimal number by looking at it in this perspective. I can do the same with octal. Remember, base of 7, the highest number we can count to is 7. So in this case, my octal number is 75, and the little 8 represents the fact that it is an octal number. So in this case, 7 times 8 to the power of 0, so the same as 7 times 1. Sorry, not 7, that should have been 8, 5. I'm just going to correct that so that you guys don't get confused. All right. So we had 75, so this is 5 times 8 to the power of 0, which is a 5, and 7 times 8 to the power of 1, which is just an 8, 56 plus 5 gives us 61 in the decimal value. Now hexadecimal, same thing, except remember we use some alphabet. So A actually represents, we said, number 10. And that's our most significant number. And then 4, and then 9. So 9 times 16 to the power of 0 is just 9. 4 times 16 would be 64, and 10 times 16 times 16 would be 2560. Add all those together, my decimal value would be 2633. All right, let's go a little bit deeper into this. So what we're going to have to do is often convert back and forth. And so right here, I want to take a binary number to a decimal number, and then a binary number to an octal number, and a binary number to a hexadecimal number. So in binary, every digit is twice the value of the last digit. So if we look at this, examine this, and so 1 times power, or 2 to the power of 0 is 1. Then 1 times 2 to the power of 1 is 2. So 2 is double that. Then 1 times 2 to the power of 2 is 4. And you'll notice that as we go up, this always doubles. So 1, 2, 4, 8, 16, 32, and you can keep going as high as you want. So one way to convert, which I already showed you, is just to add those numbers together. And that would give you 63 in decimal. Now, what happens sometimes is that we don't have a value in our binary number. For example, down here, my binary number is 11011 in binary. So in that case, I don't have a value because it would be 0 times, so that's my third 1, 2, 3, 1, 2, 3, that's my third significant number. So if I had a 0 here times 2 to the power of 2, that would be a 0. So I wouldn't add anything in for that one there. So for this one, I use the this codex, I call it. So 1, 2, 4, 8. I'm going to put that 1, 2, 4, 8, 16 here. But for this one, because that's a 0, it ends up as a 0. So I can add all of those other ones, and it ends up as a decimal number 27 decimal. You could also use your calculator for a bunch of these. Make sure your calculator's in mode 0. You would go second function, find the binary button, put in your binary number 11011, go second function again, and then find your 2 decimal, and that will give you 27 in decimal as well. So that was just proofing what I did with the codex addition now. Now if I want to go binary to octal, I'm going to break my binary number into groups of 3. Remember, a group of 3, if we look at it, let's say we had 3, and it was 1, 2, and 4. The highest that number you could get to is adding those 3 numbers together is 7. And we know that octal, the highest you can count to is 7. So we use groups of 3 to quickly convert between binary and octal. And the way we do that, here's my binary number, same one I used up there, 11011. I take these first 3, group them together. I add the codex value for any of the ones that I call, these are called turned on. So in digital or computer language, a 1 is on and a 0 is off. You all might also hear it called high and low. And so in this case, if it's turned on, I can add the 2 and the 1, and I get 3. And then for this group of 3, notice it's only 2 there, but if I pencil in the third one, it's not going to make any difference anyway because it's a 0. And so that group of 3, I would only be using the first 2 digits here. So I'd be adding the 2 and the 1 again, and I get 33 in octal. I can double check that using my calculator. So make sure you're in mode 0 again, second function, to the binary number, enter the binary number 11011, second function to octal, and you'll prove that 33 is the answer in octal when we convert it from that binary number. This next one is binary to hexadecimal. It's the same idea, except in this case, we're going to break into groups of 4. So down here, I have my binary number, and you notice that I've taken this group of 4, put them together. I don't have 4 over here, but I can pencil in 3 more that won't make any difference to my final number because they're zeros anyway. And so over here, I have a 1, a 2, and an 8. Those are all turned on or high, and I can add those together. So 8, 2, and 1 is 11. But remember, in hexadecimal, 11 was actually the B. So my second number here is going to be a B, and then my first number was just a 1, and so 1B in hexadecimal. I can prove that with a calculator. Second function, go to binary, enter my binary number 11011, second function to hexi, and there it kind of spits it out in a weird looking small b instead of a big B. That's just what the calculator can actually give us. But it's 1B in hexadecimal. I can double check another way too, and that 1B in hexadecimal is B is 11 times 16 to the power of 0, which is just 11. 1 is 1 times 16 to the power of 1, which is 16. And I can add those two together, and I get back to 27. And up here, we knew that 11011 in binary converted to 2710. So we've kind of gone the full loop with that. This next one is just carrying on with another example of how to go from decimal to binary. So to convert from decimal to binary, we're going to start with the binary codex. Down here I have that 1, 2, 4, 8, 16, 32, 64, and you can keep going. Starting on the left, so what I'm going to do is I'm going to convert this 75 in decimal to binary. I'm going to end up with this number in binary. So 75 decimal. What I do is I take it over here and I take it as far as I can to the left or to the most significant values in my codex, and I subtract this codex number. I don't want to go any further because the next number would be 128, and I can't subtract 128 from 75. So you have to start where you can subtract. So 75 minus 64 leaves you with 11. So I call that the remainder. You're going to move the remainder over there. What that's telling me is that I can get one group of 64 out of that number. So I am able to turn on this value in my binary number because I was able to subtract and get a group out of that. I take my 11 over. You'll notice that I cannot subtract 32 from 11. So I put an X there and I put a 0 there. I didn't get a group out of that. Move that 11 over again. 11 minus 16 is not possible. So I got a 0 down there. Move the 11 one more time, and now we can subtract 8 with a remainder of 3. We're going to take the 3 up top next door, but don't forget to turn on one of your binary numbers below that. Now 3, you cannot subtract 4 from 3, so that's not going to be turned on. Move that over one more. You can subtract 2 from 3. Gives you a remainder of 1. You're going to carry that. Don't forget to turn this guy on. And now 1 minus 1 will be 0, and we can turn on this number 1. So that's my binary number. I've converted 75 decimal to my binary number, and I can double check by adding those all up. So again, using my codex, 1, 2, 4, 8, 16, 32, 64. Only the ones that are turned on are carried down here. If there is 0 there, there's 0 here. So 64 plus 8 plus 2 plus 1 will give me 75. That's one double check. The other double check is my calculator, second function, 2 decimal, put in the 75, second function, 2 binary, and yes, it ends up being the same number. We can also work on just going octal to binary and hexadecimal to binary. So for octal to binary, we're going to use groups of 3 again because octal only counts to 7. And here's my octal number, 613. I'm trying to convert that to a binary number. And so each of these digits is represented by 3 of my binary numbers. So 1, 2, 4. The 4 is not turned on, but I add the 2 and the 1 to represent the 3. Here I have 1, 2, 4, but the 2 and 4 are not turned on, and my 1 represents that 1. Here I have a digit of 6, value of 6, so I need to turn on the 2 and the 4, add them together to represent that 6. So my binary number is now this number 110001011. I can double check that using my calculator, second function to octal, put in my octal number of 613, second function to binary, and there's my binary number, matches that guy. This guy here is hexadecimal to binary. We said we use groups of 4. Each group counts to max of 15. Hexadecimal has a max of 15 count. So in this case, I've used C28E as my hexadecimal number. I'm going to represent each value in my hexadecimal number by a group of 4 ones and zeros, and those are going to end up being my binary number. So 1, 2, 4, and 8. The 4 and 8 are turned on because C is a value of 12. Here, just the 2 is turned on to represent 2. Here, just the 8 is turned on. And here we needed an E, and so 1 is turned off, 2, 4, and 8 are all turned on to represent 14. This one's tricky. This one is too long to show up in our calculator. Our calculator can only spit out 10 digits. And we have 4, 8, 12, 16 digits there. So we cannot use our calculator to figure this one out. Yeah, so that's how you convert to those values. And got one more example here. There's another computer encoded value that is sometimes used as a shortcut. So it's called binary coded decimal, or BCD. It looks like binary. That's why they call it binary coded, but it's not actually the same value. And what they do is they take a decimal number and they just shortcut it and give it the same idea. We're returning 2 and 4 on to add up to 6, and we're turning 4 on to represent that. But this is now then going to have a BCD written beside it. And it's not the same as binary to decimal. It doesn't end up being the same number. For example, I take that same number, 46 decimal, and I use our way of converting from decimal to binary. So here's my codex, 1, 2, 4, 8, 16, 32. I take my 46 and I subtract 32. 14 remainder goes over there. I do have a group, so I turn that on. 14 minus 16 is not possible, so I put a 0 there. Move the 14 over. 14 minus 8 gives me 6 remainder, and I do turn that on. 6 minus 4 gives me 2 remainder. Turn that guy on. Take my 2 remainder over there. 2 minus 2 is 0. Turn that guy on. I can't subtract that, so that's a 0. So my binary looks different than my binary coded decimal for the same number. And here it is together. So for 46 in decimal, to get to binary coded decimal, it gives you this set of zeros and ones. If you take that 46 and in decimal and turn it to binary, you'd end up with this set of numbers. So just be careful. Binary coded decimal is a shortcut to be used, that they use in computers, as a quick way to get to give us a zeros and one values, because that's what our computers work on. And we did notice that this is a bit more cumbersome than this, and that's why they came up with the binary coded decimal, because otherwise it's a bit more cumbersome to arrive at a binary number for a decimal. I hope that helps, and look forward to sharing some more with you.